Welcome back. In this video, we're going to look at another example of cool programming. This time, let's move beyond the simple hello world kind of examples and on to something more exciting, say the ever-popular factorial function. So, in order to write factorial, we'll need to open up a file in which we can write some code. Let me start that. And recall from last time that every cool program has to have a main class, and the main class is required to have a main method. And we don't care what the main method returns, so we'll just have it return something of type object. And let me just fill in the skeleton here of the file. And so now we're ready to write some code. So what are we going to have the main method do? Well, before we can actually write factorial, before we can get to the guts of this program, which is actually not very difficult, we need to talk about I/O some more, because we're going to need to be able to read and write numbers. We're going to be able to read numbers from the user who's running the program and print them back out. So let's just review a little bit about I/O. So in order to invoke the I/O functions, we need an I/O object. And one of the I/O functions is something that prints out a string. So let's just write a program that we already know how to do, just to confirm that we remember that. And now we can compile this program, and it should just print 1. And let's see, indeed it does. Okay, so it prints out the number 1. And so now let's come back here, and let's talk about how to do input. So instead of just printing out the number 1, let's print out a string that the user types in. So in here, we're going to read a string. And in order to do that, we need an I/O object, because there is another function, another method called inString. Okay? And so this will read in a string and return a string. And then to make sure that we get the nice output, let's concatenate onto that string a new line. So this is just to, when it prints the string back out, it'll be printed on its own line. So let's try compiling this. And mistake. It compiles, and now we can run SPIM. Remember, the bang command in Unix runs the previous command that began with the same letters. And now the program runs and it waits, because it's waiting for me to type something. And if I type in 1, it prints back 1. And if I type in 42, it gives me back 42. All right, so now the next thing we need to talk about is how to convert strings into integers, because if we're going to do factorial, we want to work on integers and not strings. And at the moment, we're just reading and writing strings. So there is a library written in Cool that does conversion between integers and strings. And we're going to give the main class here the functionality of that class, which is called A2I for ASCII to integer. And that defines a bunch of methods that can convert between strings and integers. So let's add those commands in here. So here, here's our string that we've read in. And what we want to do now is to convert this into an integer. So let me just add a couple of parens here. So there's our string. Okay. And now we're going to invoke on that the method, we're going to call on that the function, the method A2I. Okay, and let's just double check here that we've got parens in the right place. So that's the argument to A2I. Now recall that when we have a dispatch to a method and it's just sitting by itself with no object, it's a dispatch to the self object. And the self object is the object of the current class that we're in this case, the main object, which has inherited the A2I methods. And so the A2I function should be defined in there. Now we have an integer, and we can do something with that integer if we like. So let's add some more parens here, and let's say we just add 1 to the integer. Okay, and then once we're done with our integer, whatever operation it is that we want to do on the integer, we need to convert it back to a string so that we can print it out. And there's an inverse function I to A that will do that. So I don't know if we have all the parens in the right places at this point. So let's just check. Yes, that looks like that should work. So this will read in a string, convert it to an integer, add 1 to it, convert it back to a string, concatenate on a new line, and print it out. And let's see if all that actually works. So let's run the compiler, and we got a problem here. It says that we have an undefined class A2I. And the reason is we didn't supply the code for A2I. So if we look in our directory here, we'll see I've already copied in the class file for A2I, and I encourage you to go and look at that code. It's actually interesting code to see how the conversions are written in Cool. But now we need to talk about how to compile a program that uses a library. And the way you do it is very simple. You just list all the class files on the command line when you call the compiler, and it will read them all in and treat them as a single program. So in this case, we compile fact together with A2I, and that compiles. And then we can run it. And now, if I type in 3, it prints 4. And if I type in 1, it prints 2. And so the program seems to be working. And now we're almost ready to write our factorial function. So what do we want to do in factorial? Well, we want to do something other than just adding 1. Instead, we want to call our special function factorial. So let's insert a call to factorial in here. Okay. And let's get rid of the +1. And then let's check that we have all the parens that we need. So we need to close off the A2I call, the factorial call, the I2A call, and then that last one should be the outstring call, and it is. Okay. And so now we can add a method fact to this class. And fact is going to take an integer argument. So we need a parameter here, and its type is int, of course. And the whole thing is going to return an integer. And then we need a body of our function. And probably a good idea here, just to make sure that we got this much right, to do something simple. So let's just try to make a function that returns 1 more than its argument. So this will do exactly the same thing that we had before. And let's just confirm that that is working. So we compile with the A2I library, and now we have a syntax error. And we see that I forgot the closing semicolon here for the method. Remember, the class body is a list of methods, and each method is terminated by a semicolon. Let's try compiling that again. Now it compiles. Let's run it. We type in 4, it gives us back 5. All right, so it looks like we're ready now to actually write the code for factorial. And this is going to be anticlimactic because it's actually very simple code if we write it recursively. So let's do that. So how is that going to work? Well, everybody knows the definition by heart, I hope. If I is equal to 0, then the factorial of 0 is 1. And we need a keyword there, then 1. Otherwise, the factorial is going to be I times the factorial of I minus 1. Right? And then if statements in Cool always end in the keyword phi. So it's an if then else phi construct. And that is actually the entire definition. So now we should have a program that actually computes factorial, and it compiles. So now let's run it. So factorial of 3 is 6, and factorial of 6 is 720. That looks right. And if we try it one more time with a bigger number, we get a large number. We think that's probably correct. And so anyway, our factorial function is working. So now let's come back here, and just as an exercise, let's rewrite this code iteratively. So instead of using a recursive function, let's write it using a loop. And in order to do that, I'm going to get rid of that code. What are we going to need? Well, we're going to need an accumulator here. We're going to need a local variable that we can use to accumulate the result of the factorial computation. And the way you declare local variables in Cool is with let statements or let expressions. So we're going to have, let's call this variable fact for the result of factorial. And notice here that I can have a variable that has the same name as the function. And the programming language Cool will not get confused about that because variables and functions play different roles. So we'll have factorial fact, it's of type int, and we need to initialize it to 1. All right, so that multiplication will work. I think the default for integers is to be initialized to 0, and that would not be good if we're going to be multiplying up fact with other numbers. All right, so then a let has 2 parts. It has the variable or variables that you're declaring. This could actually be a list of variables. We only have 1 this time. And then it has a body, the expression or the computation in which the fact variable is available. And what do we want to do? So I think we're going to need to have this be a statement block, because we're going to need to have more than 1 statement in sequence, and we'll see why in just a minute. But then we want to have a loop. And so what is our loop going to do? Well, we're going to say while I is not equal to 0, what do we need to do? The opening for the loop body, the opening keyword is called loop. And now I think we're going to need another statement block here. So let's open up a block. We're going to probably need to do more than one thing. The first thing we want to do is we want to have fact be fact times I. Okay, so we know that I is not 0, and so we need to multiply the current value of I into fact to accumulate the result. And then we want to subtract 1 from I. And notice that the assignment statement in COOL is this backwards arrow. That's how you do assignment. It's also how you do initialization. So initialization and assignment look the same. And then we can close off our statement block. Okay, so the body of a while loop is always a single expression. In this case, that expression is a block that consists of 2 statements. And then we can close the loop. And the closing for a loop is the pool keyword. And then now we're in a statement block, so this has to end with a semicolon. Notice the statement block up there from the let. And now we want the result of the let block, or the let expression, to be factorial. So whatever we got out of the while loop, whatever we computed in the while loop, we want that to be the result of the entire let expression. So that's the last statement of our block. Remember, the last statement of a statement block is the value of the block. The body of the let is the result of the let, so the fact will also be the result of the whole let statement, since it's the result of the statement block. And since the body of the factorial method itself is just the let expression, fact will be the result of the whole thing. And so this, if we've haven't made any mistakes, should be an iterative version of factorial. So let's compile this. And amazingly, it compiles on the first try. And now let's run it. And whoa, it actually works. So we got 6, and let's just do one more test to see that, to convince ourselves that things are working reasonably well, and they are. Now let me just point out one common mistake that you can easily make, and that I make when I haven't written cool programs for a little while. If you're a C or programmer or a Java programmer, you might think about writing assignments like this. So you just use the equal sign to write assignment. That looks completely fine if you're familiar with those languages or used to programming in those languages. And now let's see what happens when we try to compile this. Oh, it compiles just fine. And then what happens when we try to run it? Oh, well, it runs, asks for an input, so let's give it an input, and then we see that we run out of heap. And that looks like an infinite loop. So we're going around and around the loop and consuming memory for some reason, and we'll get to that much later in the class, why this loop actually ends up consuming memory. But clearly we don't have enough memory in the loop, and eventually we run out. And so that's a sure sign of an infinite loop. So what's going on here? Well, the thing is that the equals operator in COOL is the comparison operator. So up here, so we compared I with 0, and that returns a Boolean. So these are perfectly valid COOL expressions. They just happen to be Booleans. And so you don't ever actually update I or factorial in this program. You're just comparing fact with fact times I and I with I minus 1. And the program is perfectly happy to do that. It just doesn't compute the factorial function. And it never terminates because I never reaches 0. So that concludes our factorial example, and we'll do one more example next time of a more complicated, of a COOL program with some non-trivial data structures.